Welcome. On this video, we will talk about function composition. So let's get started. Let's start by discussing this small introduction, which it will illustrate what function composition is. So it states, for the following example, here we have a function, which we're going to call f of x. And here we have a second function, which we're going to call g of x. And now it says the following notation illustrates the function composition. So this is the notation that we'll be using for function composition. And this is actually the result of what we're going to do, which we refer to as function composition. And now the question is, what exactly happened here? Like, what do we mean by a function composition? The first thing that you might notice by the notation is the following. Notice what this is trying to say here. This is saying we are substituting g of x into f of x. So what we're doing is we're looking at the function of f of x. And every time we encounter a variable, which in this case, the variable seems to be x. Every time we encounter the variable of x, all we're doing, we're substituting the function of g of x. And notice that's exactly what just happened here. So let's just do it here from scratch. So here we have our function f of x. And now the notation f g of x, it's saying every time I encounter a variable of x, I'm going to substitute it with the function of g of x. So here I have a variable of x. My function of g of x is 3x plus 1, so I'm going to substitute that. Plus, again, notice that here we encounter another x. Plus 2, and notice that this is the same expression that we got here from our small introduction question. So the idea of composition is the idea of substituting or evaluating one function with another function. Which in this example, we evaluated the function f of x with the function of g of x. And now, there are two ways that we can write down our notation for composition. This is the way that we have written it in this small example, but we could have also written in this way. And usually, if we're going to write down notation of composition using this second way, we just read it from right to left. So here we're looking at g of x and then f of x. So this is saying I'm going to take a look at the function of f of x, and I'm going to substitute it with the function of g of x. So let's just do some examples, because this was just a small illustration of what we mean by this notation. So let's do some examples here. Okay, so here we want to create a composition. Notice that this is the notation of composition. And the way that we're going to be reading this composition is we're going to be taking a look at the function of f, and we're going to substitute it with the function of g. And notice that here, this is how we are defining our functions. Here we have f of x, and here we have g of x. So I know that the composition f composed of g of x, another way of writing it is just the function of f evaluated with the function of g of x. Which another way of writing it is actually write down explicitly what g of x is. G of x is x minus 1. And now, what we're saying here is I'm going to take a look at the function, and I'm going to substitute it with the expression of x minus 1, which is the expression that g of x was defined on. So where's f of x? F of x is just the square root of x. And every time we see an x on the square root of x, which we do have it here, I'm just going to substitute it with the function x minus 1. And this is it. Our composition of f composed on g, it's equivalent to just the square root of x minus 1. Now let's see, is it possible for us to start evaluating some of those compositions? Now, what we mean by this type of notation is the following. We're going to define the composition, which we already have it here, and we're going to evaluate it by 2. So here we're saying we're going to evaluate the composition by a value of 2. So let's do that. We already know that the composition is the square root of x minus 1. But since we want to evaluate it at a value of 2, now we're going to substitute the actual variable, but now with the value of 2. And now if we simplify this is equivalent to just the square root of 1, which is just 1. So in this case, it is possible for us to evaluate the composition at a value of 2. So one way to understand this is first define what the composition is, which we already have defined it here. And now just evaluate your composition with the value of 2. So now we have another example here. Now we want to perform the composition of f of g, but now evaluate it at 0. So what we're doing here, we are evaluating the composition by a value of 0. So let's do that. Let's get our composition, which we have already defined it. But now notice that we want to evaluate it with the value of 0. So every time we see an x in our full composition, we're just going to substitute it with the 0. So let's do that. So now we got 0 minus 1. Which in this case, we just want to deal with just real numbers. Because remember that the square root of -1, that's an imaginary number or a complex number. Where in this case, we want to just restrict everything to real numbers just in this lesson. So we're just going to say that it is not possible. We can say it's not a real number. Because so far we have not discussed what complex numbers are. So let's just limit all of our answers to real numbers. So for this example, we're just going to say it is not possible since we just want real numbers. And the square root of a negative number, it is a complex number. So let's do a couple more examples here. Let's take a look at example B, which now what we want to do here is we want to define again. Let's try to define a new composition. So let's just get familiar with our notation. So f composed of g with the variable of x, this is equivalent of getting the function of f and evaluated by the function of g. So let's identify what those functions are. So here we have the function of x squared, and here we have our function of g, which is x minus 1. So what we're going to do here is we're going to take a look at the function of f, and every time we see an x on it, we're going to evaluate it by the full function of g of x, which in this case is x minus 1. So if we do that, it's going to look something like this. This x, it's being substituted with x minus 1 to the square. And now notice that this function, it's essentially the function of f of x, but it is evaluated by g of x. So every time we saw an x, we just substituted the whole function of g of x. And let's just keep it here. Let's not just expand it. So let's just rewrite our result. The composition of f on g, it's equivalent to just x minus 1 all to the second. So notice that all we're doing, we're just substituting a function inside another function. And that's all composition does. We're substituting a function inside of another function. And now on our next example, this example is going to help us illustrate the idea of, does the order of the composition matter? Because now what we want to do in this example is the following. Notice that here we have two different compositions, f composed of g and g composed of f. And the question is, are they similar? One way to show if they're similar or not is to actually perform that composition. So let's perform the composition of f of g of x on the left, and let's perform the composition of g composed of f to the right. Okay. And now let's see if they actually give me the same result. So let me just separate that. So I guess this would be a good line in the middle. Okay, so now if we want to rewrite this composition, another way of rewriting it is f evaluated at g. And where is f and where is g? Well, notice that f, it's illustrated here as it has been defined here as just x plus 2. And here g is being defined as 4 minus x squared. So let's evaluate and let's compare. So on the left-hand side, we want to get the function of f, and we want to evaluate it by g. So in our function of f, every time we see an x, we're going to substitute it with the whole function of 4 minus x squared. And if we simplify this, let me just drop the parentheses, we're going to have 4 minus x squared plus 2. And if we simplify this, we're going to end up with negative x squared plus 6. So this is how the composition of f composed of g, it's been defined as just negative x squared plus 6. Well, do we get the same result if we switch the order? Well, let's see. What happens if we get the value of g and we compose it by the function of f? Again, what we're going to do here is we're going to take a look at the function of g, and every time we see an x, we're going to substitute it with x plus 2. So let's do that, and let's see what's the result. So we're going to have 4 minus, and notice that here we have an x, so let me substitute it with the whole function, x plus 2. And we still have a whole square on it. Because again, all that we're doing, we're just substituting the x, so not just the x squared. So every time we see an x, we're going to substitute it with the function. So this is what we have. And let's simplify this. Now this becomes 4 minus, and here we hold the expression x plus 2 to the second. Well, that's equivalent to x squared plus 4x plus 4. And if we simplify this, here the negative should be distributed by every single one. So we got 4x minus 4x minus 4. And if we evaluate this, notice that the 4's will cancel out. And now we have the expression of negative x squared minus 4x. So notice that this is how we are defining those two functions. So now the question is, are they similar? Definitely not. Because the function negative x squared plus 6, it's definitely not equivalent to, oh, I see that I'm missing a second exponent here. It's not equivalent to negative x squared minus 4x. They just are not. So in this case, what we want to show here is that the order of the composition matters. So even though f and g were the same of both expressions, the way that we define it, or at least the order that we have performed the composition, give us a completely different result. So that's one key characteristic of composition. The order on the way that we're going to be composing those functions are going to give us different results. There are specific examples where perhaps if F and G are the same, it doesn't really matter the way that you compose them, you're still going to get the same result. So there are very specific examples that perhaps this is not true, but generally speaking, the order of the composition does matter. So let's just recap everything that we have discussed today. What we have done today is we have defined what a composition is. A composition is whenever we define a function inside of another function. We have seen different examples on how we can define composition. And very important, this is a very key characteristic of composition. The order of the composition matter. We just saw here that there are two different completely results, and the only difference between those two results are the way that we compose and the order of the composition. And I'm aware that perhaps here we have not completely finished the example because it says, well, are they the same whenever x is 0 and 1? We can leave that as an exercise for you to practice on. And with this, it concludes our lesson for function composition.